Hello everyone. Now in this lecture we will start something new about the connections. In previous lectures we have discussed about the connections, which is bolted connection and welded connection. So in steel structure, connections are most important as compared to RCC, because here in steel structure we have all the members are available in market, that is ready made, which is manufactured in companies. So whenever we are going to design the individual beam, individual column of steel structure, then we will bring that members from the company, and the important task, that is we have to fabricate that member on site with the help of bolted connection as well as welded connection. So as we discussed in our introduction chapters, at that time we have discussed that whenever the steel structure is designed, we are going to design the members first, and after that we are going to connect them. Here we had studied first connections, and now we are going to design a member. So the task of the designing of member, in that case we have lots of type. In that, some of the members are reacted due to tension, some of are in compression, some of are in bending. So we have to finalize that thing कि यहाँ पे कौन सा फोर्स इस पर्टिकुलर मेंबर में आ रहा है, एंड दैट इज डिपेंडिंग ऑन द एनालिसिस. So whenever our analysis part is over, then we must have to design that member individually. So in that case, whenever we are talking about the truss members and foot over bridge, so in that case forces are acting in our member as a tension and as a compression. So for that we have to design that member as a tension member. Now we are going to discuss about that tension member. Clear? Okay. So the introduction of the tension member, that is, tension members are subjected to axial tensile load which tends to elongate the member. A member is in pure tension can be stretched up to and beyond the yield limit without local buckling. Means whenever our member is acted upon by the tensile force, then we have to design that member up to its elastic limit or beyond its elastic limit, means it is up to the FE 410, means FU is equal to 410, right, without buckling. That is the design part. Now which are the tension members? कौन कौन सी जगह पे टेंशन मेंबर्स हो सकते हैं? So first one is component of trusses, as I shared just before. Sag rod, that is used in purlin and it is used in industrial building, the shade. Bridge trusses, suspenders, cables stayed bridge that we have seen lots of time. Cable stayed bridge, transmission line tower, right? ट्रांसमिशन टावर लाइन आपने देखा है, दैट इज स्टैंडिंग इन आवर गार्डन, SSIT, है ना? गुड. नाउ communication tower, that is Vodafone tower and all that things. Wind bracing system in multi-storied building. Whenever we are going to design high-rise building, at that time we are going to provide in that buildings bracing for the stability of the structure. So in that case, some of the members of bracing are cause tension and some of are compression. So here these are the some of the steel structures and where the tension members are applicable. So here this is a truss, and in truss all the joints are pin joints. So there is no bending in any member, only the members are in tension or as well as in compression. This is our ties, truss ties. Again the same thing, it is in tension or it is in compression. This is a sag rod which is below the here our roofing material, that is galvanized iron sheet. This is our principal rafter. In between there is a purlins over here, and that purlin is connected by sag rod. So sometimes these sag rod are in tension. This is cable stayed bridge that we know. Now a tension member is also called as a tie member or simply a tie. When a tension member is subjected to axial tensile force, when the distribution of stress over the section is uniform, the complete net area of the member effectively used in the maximum permissible uniform stress. Therefore, a tension member subjected to axial tension is said to efficient to economical member. Means whenever we are going to design any member, that it must be economical as well as it can stress uniform and the cross sectional area that enough to resist that much tension. Clear? Now the strength of tension member is influenced by length of connection, size and shape of the fastener, means bolt, net area of cross section, type of fabrication, connection eccentricity, shear tag. Now the most important thing, that is type of tension member. Which type of tension member we are going to take in our design? Type of structure and method of connection decide the type of tension member. Here the various type of tension members used may be grouped into the following: single structural strip, that is rolled section, compound section, built up sections, rods and bars, and wires and cables. Means here some of the members are directly used by us. हम फैक्ट्री में से जो भी मेंबर्स मंगवाते हैं वो डायरेक्टली यूज़ कर सकते हैं, बिकॉज वहाँ पे टेंशन हमारा कम होगा. बट कंपाउंड सेक्शन, समटाइम्स वी हैव टू मेड अप दैट सेक्शन ऑन साइट विथ डिफरेंट एंगल्स, members, something else. Built up section, आई सेक्शन सपोज हमें बनाना है, तो हम क्या करेंगे? आई सेक्शन हमें रेडीमेड भी मिलता है, बट हम साइट पे भी आई सेक्शन बना सकते हैं विद द हेल्प ऑफ 3 प्लेट, 2 फ्लैंजेस एंड 1 वेब, राइट, रोड्स एंड बार्स. that we know, rounded bars and square bars, right? Wires and cables. It is most important thing to use for the taking tension in a structure. Wires are used and made up cable from there, and that we are using in a cable stayed bridge. Here some of the sections are given. In this section we can take anyone as a tension member. These are the single rolled section that is available in factories or companies. We can get directly from that and used as a tension member. L section, T section, C section, square hollow section, circular pipe, I section. These are the single section, that is rolled section. But in compound section, as I discussed, हम यहाँ पे 2 angles ले सकते हैं, back to back, 2 angle front to front, 2 channels back to back, 2 channel front to front, 2 angles something like this. These are the compound section. And the built up section, that is, this is I section, which is bring from company, it is rolled section. But if we want to make the I section in our site, then we can make it on site, that is built up section. Clear? Here this is the square or rectangular hollow pipe that can available in factories, that is rolled section. But whenever we want to make it at site, then we can. Right? This is the round bar, flat bars, cables, and these all things are used as a tension member. So whenever we are going to design a tension member, then we have that this much force must be resisted by member that we are going to design. कि इतना फोर्स आ रहा है, तो ये फोर्स को रेजिस्ट करने के लिए हम इसमें से कौन सा सेक्शन सिलेक्ट करेंगे और वो सेक्शन का क्रॉस सेक्शनल एरिया क्या रहेगा जो हमारा फोर्स, दैट इज टेंशन फोर्स, रेजिस्ट कर पाए. राइट? फॉर दैट वी हैव टू डिजाइन दैट मेंबर फर्स्ट. नाउ फॉर द डिजाइनिंग ऑफ टेंशन मेंबर वी मस्ट हैव टू हाउ मच capacity of that member and how much tensile force it can be take, that we have to decide with the help of our codes. So the factored design tension in the member shall satisfy the following requirements, that is T should be less than TD. T should be less than TD. And what is TD? TD is the design tensile strength of the member. The design strength of the member under axial tension, TD, is the lowest of the one. Means T should be less than TD. We have to find out this TD, and the T is the actual force acting on our structure. The first, design strength due to yielding cross section, that is TDG. This TD must be smaller from the number of design strength. One of them, that is TDG, the cross sectional design strength, that is. Number 2, the design strength of rupture, TDN, and third one is design due to block shear, TDB. From these 3, whichever is smaller, that is TD, and T should be greater than this TD, sorry, less than this TD. Clear? So first we have to find out the design strength due to yielding of cross section. This equation is given in IS 800, page number 32. Open that page and you can see there the equation for this tension, this rupture, and even the block shear is also there on page number 33. So whenever you are going to design any member, you must keep with you IS 800 and steel table. Without that, you can't design any members. So the equation is TDG is equal to AG into Fy upon gamma m0. That Fy we have always, gamma m0 is given on page number 30, right? And the gross area that we are going to design. Design strength due to rupture of critical section. We have number of things. It is depending on which kind of members we are going to select. Depending on that, if we are going to take plate, that the equation is TDN is equal to 0.9 AN into FU upon gamma m1. That FU and gamma m1 we know, but AN is the net area of the member. For a single angle, suppose we are going to use the single member as tension member, single angle, then the equation is something like this. In this equation is given on page number 32 and 33. This equation must be carried with that beta, AGO and ANC. This three term is very important for us. For that we must have to find out first beta, then net area of connected leg and gross area of outstanding leg. These things we have to first find out. For that beta, if the equation of this beta is 1.4 minus 0.1206, it is W by T into Fy upon Fu into Bs upon Lc. This equation gives us some value of beta that must be less than of this equation and greater than of 0.7. Clear? So refer the IS 800 and page number 32 over there, 33 over there for this. Now the next, that is rupture, that we discussed. TDN is something different from compound section, built-up section and all other sections. The TDN is equal to alpha into AN into Fu upon gamma m1. That AN is the net area and the alpha is always 0.8 is taken by us, because we are thinking that we have more than 4 number of bolts. So always we are taking 0.8 as a alpha. Now the design strength due to block shear failure. It is the most important thing, block shear failure. Whenever the force of the member are eccentric, at that time some of the portion of the plate is broken. So at that time that broken portion is due to shear. That block is broken from the member. That block is failed due to shear. That block shear must be checked by us for the designing of member. For that we have these two equations and we have to put the all values in this equation and we can get the block shear failure. This block shear failure, this rupture and the gross area, from these three we can get the TD. Now net effective area. In every equations we have the effective area and that area must be calculated by some important thing. Suppose we are going to take something like this chain bolting, at that time we have to minus the all bolts diameter from this width and multiply with that thickness, and this is the chain bolting. For each condition we have different equation and that equations is given in the code. After that we can get the net area. A plate in a joint may fail in tension through the weakest section due to the hole. The hole may be arranged in a longitudinal direction of the plate, that we discussed. So the number of hole is equal to number of rows across the width if the holes are staggered. Number of holes across the width is reduced, that we know. Now, the equations are here in case of chain bolting and in case of zigzag, means staggered bolting. So, for this, from this we can get the net area AN, and that we have to put in all our equation of TD. Clear? Now, the shear lag effect. This is the most important part. The block shear failure is connected with the shear lag. What is the shear lag? Whenever we are going to connect any member with the another member with the help of bolts, at that time the stress induced in a member that is equally spread on both the sides, but whenever our eccentric connection, at that time the stress is transferred from one point to another point, some of the portion are affected earlier and reached at FU, ultimate stress capacity, but the long portion of that member still it is up to the yielding. So, at that time that portion is failure due to shear, means the shear lag effect is connected with that block shear failure. The force is transferred to a tension member by gusset to one of the legs either by bolting or welding. The force thus transferred on the leg by one end connection locally gets transferred as a tensile stress over the entire cross section by shear. Hence, the tensile stress in the section from first bolt hole to the last bolt hole will not be uniform. That some of the portion is reached at the ultimate stress and some of the portion is still in yield stress. Then, whenever the second portion is reached at up to FU, the first portion is broken down from there. So, that is called block shear failure, and that is depending on the shear lag effect. The connected leg will have higher stress at failure even of the order of the ultimate stress, while the outstanding leg may have stress even below the yield stress that I discussed. Hence, outstanding leg is not fully effective in the region of connection. The shear lag reduces the effectiveness of the component plate that the tension members that are not connected directly to the gusset plate. Even it is done also over there, something like this. This member angle is connected with the plate, and whenever the stress is going to develop from this bolt from here to here, and it is from here to here. So, whenever the stress is distributed toward the both sides, this portion must be affected earlier at FU, and still it is because it is long, so still it is in yielding, then this portion must be fail as early. So, it is called block shear failure. The efficiency of tension member can be increased by reducing the area of such component not directly connected to the ends. This is also most important thing. In the case of angles, the equal angles with large leg connected will reduce the effect of shear leg. Clear? Now, the slenderness ratio. This is also most important part. As we discussed, हमारा जो भी member है, that member उसकी लेंथ कभी भी ज़्यादा नहीं रखनी है. Whenever we are going to design the long member, it is failure due to buckling, local buckling, outermost failure of the members, number of creation is that. For that we have to must finalize the slenderness ratio. It will give us the how to we can get the strength of member. The slenderness ratio, it is equal to the effective length of member per the least radius of gyration KL upon R. It is also we studied in structural analysis 1 in many times. The slenderness ratio is the most important part of the designing of tension member. The stiffness is not the main design criteria for the tension member, but the maximum effective slenderness ratio of the tension member shall not exceed the value in table. This is the table. In this table they have given us the how the slenderness ratio must be up to the limit of this. In the tension member we are always going to take 180. This value is remembered by us. Now for the designing of tension member, some of the steps we have to follow, and that steps are: first, compute the gross area, that is AG, required for the factor axial tension on the tension member and the yield stress. The equation, that is AG required, is equal to T upon Fi into gamma m0. It is also given on page number 32. Now from this area we are going to select the section from the steel stable or else SP6. After selecting of that section, compute the number of bolts and pitch and end distance. Bolts are normally placed along the standard gauge lines. So number of bolt is equal to T upon bolt value, that is also calculated by us in our previous lecture. Now from that we can get the minimum pitch, the diameter, end distance and all that things. Now compute the three strands of the member that we discussed just before, that is TDG, TDN, TDB. From this the smaller value is known as TD, and the design strength, that TD is greater than this T, and the trial section is okay. But if this condition become wrong, then we must have to follow the steps from 2 to 4 again and revise the section. After that, check the slenderness ratio, that is we discussed. So we can from this 6th step design the members as a tension member, and still it is clearly understood by us whenever I am talking about the some case and solve that example. Clear? Got it everybody? So the tension member is the most important part. The tension member, it as well as compression member as well as flexural design. These three members are most important for the structural design of steel structure. Once you will get these three design, it's very useful for you. Now the lug angle. This lug angle is used for the connection whenever the load is heavy and only the bolted connection are not useful, not sufficient to take that much load, then we are going to do some connection from the outside of the our thinking box. That is something like this. This is our lug angle. This angle is connected with this gusset plate, and these 4 bolts are not sufficient to connect this member. So for that we have to take 7 bolt, but the overlap length is not that much. So we are going to do one thing, that is again 3 bolt are used as a connection via lug angle. Clear? Here two lug angle are there. Simple. The connection of lug angle of the main angle member shall be capable to developing the strength not less than 40% in the excess of force in the outstanding leg of the angle members. Clear? So thank you everybody. From this you can get the clear idea about the tension member, and in next lecture I am going to discuss about the some cases with the help of example. Clear? Okay, thank you once again.